All right, canonical form. So shifting gears a little, that concludes our overview of Boolean algebra, although we're about ready to go into a lot of other aspects of it, but we're not going to delve any deeper into how to prove things or theorems or whatever. Instead, we're going to look at a canonical form, which is basically, instead of canonical, just think a standard that people agree to. And the reason why we want this standard that everyone agreed to is so that we can start manipulating the circuit expression in a programmatic way. Why would we want to do that? Because if you can edit a circuit in a programmatic way, you can then write a program to do it for you, so you don't have to do the work manually and write it up on the board. All right, so we're going to go through a lot of terms, and they're going to seem completely random, and then all of a sudden, at the very end, if we get to K-maps, it'll just magically make sense and why we're doing this. So, canonical form, standard form, so we can manipulate it, minterms and max terms, we'll get to that, and then we'll talk about the sum of minterms, product of max terms, and then conversions between the two. Great. Good morning. All right, so I just said that, used for explaining it. So minterms are ANDed terms with every variable represent either true or complemented form. In other words, if you have two variables, x and y, there are four total combinations. So there are four minterms for two variables. You can have x and y, you can have x and not y, you can have not x and y, or you can have not x and not y. There are four minterms for two variables. All right. Max terms, minterms. And why are we using the word min? Because when you AND something, it tends to go to 0, as in you're minimizing it. So maybe that'll help you with understanding minterms. On the other hand, max terms are when you're ORing things together, and ORing tends to want to increase to a higher value, aka 1, so you can think of it as a max term. It is the same exact thing, except for you're ORing instead of ANDing. So we have x or y, x or not y, not x or y, and then not x or not y. Okay. All right, well, hang on to that for a moment. We want to index these so we can represent them. And we're going to say index 0 will represent on the midterm not x and not y, and then for max term we'll have it x or y. Why are we choosing this? Because it ends up, when we're done studying this, that this is very useful in optimizing a circuit if you arrange things in this order. So this is by convention. We're still defining what we want. So we have an index. All right, great. Standard order. So for minterms and max terms designed with the subscript. Will they start using the subscript? No. All right. So so if you have a function of x comma y, and it's equal to now I always forget which one's lower and which one's upper. The minterm is probably lower, isn't it? All right, yes, good. If you have minterm of 0, that means your function is that. Okay? If on the other hand you're saying f of x comma y is equal to the minterm of 0 ORing the minterm of 1, then you're saying it's not x, not y, or 1, which is not x and y. All right. Which, by the way, for those of you observing, you can take the not x out and you'd have or y, which just equals not x. But we'll get to all that in a bit. Oh, person online, sorry. There you go, everything I just said. Okay. So we want to put it in a standard order, and I wrote the standard order up on the board. And so let's see. Subscript is a number corresponding to the binary pattern. Hopefully we'll get to the binary pattern soon, because the index ordering actually will help you in identifying what it should be. Let's see, all variables will be present in minterm and max term will be used in the same order alphabetically. Yeah, okay, so ABC, let's see, max terms A or B or not C, and then A or B or C, correct. So when you're listing them out, you always want to put them in the order that they're listed to begin with in your function. In other words, it does happen to be true in that case, because, in other words, don't flip the order when describing. Don't do that. Okay, and max terms are going to be the same thing. All right, great. So the index, let's see if we can get to the binary, because that helps a whole lot more. Perfect. So here's what you want to see. So remember that we did for 2 variables. You can do it for 4. And if you have 4 variables, there are going to be 16 total possible minterms and max terms. If you convert your index to binary, it will tell you which variables are knotted and or just regular. For example, if you have a bunch of zeros, your minterms are all complemented, but your max terms are normal. If you have all ones, then your minterms are normal and your max terms are complemented. So let's go 0, 0, 1. Notice here it was not A and not B and not C and D. So the max term here would be A or B or C or not D, because the 1 represents complementing in a max term and the 0 doesn't. All right, how about this one right here for 3 on the minterm? Go for it, guys. You got this.
Not A or not B or C?
Not A and not B, and C and D. Right. Okay. By the way, I forgot to mention, in case this is confusing, these are complementing the variable. They're not some division between the lines. I know that can be a little jarring looking at this slide, but that's how it is. All right, how about this guy right here? For 7, the minterm 7.
Not A and B and C and D.
All right, we're doing great. How about now the max term for 13 in a 4 variable max term? There we go.
Would that be not B, not A?
Not A,
B,
correct.
C, not D?
Right, so not A, not B, I'm sorry, not A or not B or C or not D. Okay, wow.
That's
How, huh?
That's a mouthful.
It really can get, well, saying it gets hard. But when you index it this way, you're going to find out things are going to get a lot easier. So how are we doing? Just keep throwing, we're going to keep throwing stuff at you, and then it'll come together in the end. All right, De Morgan's law, there is a nice correlation between this. Since the complement of A and Y is the complement of X or the complement of Y, aka not X or not Y, the minterms and the max terms happen to complement one another, or in other words, be the not of each other, or the opposite you could think of, which will turn out to be very handy later on. Which is also why we chose that indexing method, because by indexing it that way, the minterms and the max terms are now complements of one another. Because if you go back here and you did it the other way, then obviously where you had x, y up here, then they would not be complements of each other, and that would not be helpful. But making them complements of each other will be very helpful in a little while. All right, the function tables. Well, since they're complements of each other, the truth tables are going to be the exact opposite of each other. Well, let's go take a look at this. When you're doing minterms, remember you're anding because you're trying to go to the minimum. So what do we have? We have not x and not y. Well, that of course is 1. But if anything else is 0, then they're all zeros. So basically, you just have this diagonal of 1s where the values end up being both equal to 1. The OR is, of course, the opposite, where only the values that are, when they're all knotted, do you have zeros, but each of these are going to be 1. Does this table make some sense? Do I need to write any of these out? All right, let me write one out. Which one do you want me to write out?
Literally any of them.
Literally any of them. All right, we'll do M2 of 0, 1. So M2, sorry, what is that? Well, it's a max term, so the 1 will signify what's complemented. The binary of 2, 0 is 0, I'm sorry, of 2, sorry. The binary of 2 is 1, 0 is what I'm trying to say. So 2 in binary, 1, 0. So that means the x, and since we're doing a max term, that means the x is complemented and the y is not. All right. Then if we're evaluating for the value 0, 1, and we're saying that x is 0, well, 0 not or 1, whoops. Of course, that equals 1 because, well, you're ORing 1, so it has to be 1, and not 0 is 1, and you're ORing it again, so it has to be 1. A little clear? That's how we get each individual piece. All right. Wow. All right. Ooh, I need to get wash my hands or something. Okay. So each minterm has one and only one present in the n squared terms. All right, all their entries are 1, right. So this is just saying what I just said. If we implement a function by ANDing the max terms to 0 entries, all right. So basically what this slide is trying to tell you is now that we have minterms and max terms, we have a method to have another canonical form or standard form known as a sum of minterms. Let me scroll back. Remember, the sum of minterms are all ands, so you're all ORing a bunch of ands. Or you can do the product of max terms where you're ANDing a bunch of ORs. This is going to make a little more sense when we go to a picture. Hey, good example. So this is a sum of minterms. They're using the word sum to replace that plus, which is really an OR. I know that'll get a little confusing, but that's how they decide to go about it. So the sum of minterms with 3 variables is equal to this. Why is that the case? Well, m sub 1, remember it's a minterm, so it's describing what's normal. So there's 2 zeros in the beginning, so the x and the y are complemented, and the z is normal. And you're ORing, you have m4, gives you this term because it's 1, 0, 0. So x is normal, the rest are complemented. And then m7, it's 1, 1, 1, so they're all normal. All right, everyone doing well at how we got from here to here? So this is called a sum of minterms, and this is a standard form. And you could write out the entire truth table if you want to, and there it is. All right, how about this one? Ooh. All right, what's minterm of 2 going to be?
0.
Okay, I'll do the first one. Not A, not B, not C, D is normal, not E. Because that is 1, 0 in binary, and since it's minterm, it's only describing the one that's normal. How about 9?
Not A.
Yeah, you're right. Not A.
Not B.
9. So that would be 8, 4, 2, 1. I forget y'all don't have my
No, it's my
immediate ability to convert things to binary.
I just blanked on that one.
0, 1, 0, 0, 1. 8 plus 1 is 9. So it's not A, B,
Not C. Not D. E.
let's go to the next one. And 17, converted into binary is 1, 8, 4, 2, 1. Because the first one's 16, sorry. So what is this one?
A, not B, not C, not D, E.
And that's a 3 or a 23. And that will be 16. Do we need to add 8? No, you're actually adding 7. So that's just, so it is A, not B, because that's the 0.
C, G,
C, D, E. How are we doing?
So, do you just by convention make the in order or is it like alphabetic or? Like
Yes, by
sign?
convention, these binaries need to be in alphabetical order. Actually,
Okay.
it's not alphabetical order. Let me be very
Or is
clear.
the order which is?
The order is defined when your function is defined.
Okay, so the first value would be.
All be A, next one's B, next one's C, next D, then E.
Should we do
This
1,
needs
2?
to be here,
Okay,
because that tells you the order that these minterms are describing each term.
so the last term should be a 1 bit, should be 1, I'll make sure I'm reading it left to right. So it's like the A is the highest value bit?
Yes.
Okay, that's why it reads exactly like the.
Left to right, yeah.
That's what I was, okay. Yeah. So if it was a different set of letters, if it was like C, D, A, it would be
Right, so for
whatever.
example, they did X, Y, Z here.
Yeah.
Yeah, look at that. And now they're doing max terms.
Okay.
So notice that they are ANDing the max terms, so you're ANDing OR groups. Since the ORs are grouped, they need to be in parentheses because of the precedence rules of AND over OR. So where's my pointer? M sub 0, so naturally there's no complementing, so it's X or Y or Z. Sub 2, well that's the middle bit, so X or not Y or Z. 3, it's the last 2 bits, so it's X or not Y or not Z. 5 is 1, 0, 1. So it'll be not X or Y or not Z, and then 6 is going to be 1, 1, 0, so not X or not Y or Z, and you're ANDing each one of them. All right. Hey, a truth table if you want to truth table it out.
And then was multiplying in orange term.
What do we got? Max term of 3. I don't know why I wrote name, but I certainly did. 3 and max term of 8 and max term of 11 and max term of 14. Boom. All right. Ooh, that's nice and fuzzy.
There we go.
So max term of 3.
So it should be
A. Which one, sorry? I couldn't hear. A or someone was saying it. Were you saying it?
I said B.
B, thank you. I just couldn't hear you.
Not C.
Yep.
B. Oh, wait, no, not D.
Not D. All right, how about this one?
Not A. D. C. E.
Make sure you say the ors. When you don't say anything, and is implied, but when you say or, you gotta explicitly say the ors. All right, you're doing great here. So 11, that's gonna be 1, 0, 1, 1. I think, yes. Yep.
So not A, or B, or C, or not D.
Or not C, because that one's on. And the 14.
Not A. Or
How we doing?
Okay, so this one's inverted, right?
No, this is the yeah, okay. In this one, the 1 signifies complement.
Okay.
And the
that's
other
what
one,
I'm
the
trying-
0 signifies the complement.
Okay.
So it depends on, when you say inverted, depends on what you mean by
Okay, I
inverted.
meant just like.
It's inverted from the previous one, yes.
Yes, I meant like it's, the not means true.
Sure. Well, sure. Anyways, continuing on. All right, so any Boolean expression can be expressed as a sum of minterms. You basically, this should be obvious, you just distribute everything out and you eventually get it. For example, down here, if you have something that looks like this, you distribute the x's out and eventually you'll get all the terms. And you will eventually get them all to ands, oring a bunch of ands. All right. So, since you can always, oh yeah, also, notice that the function may be x plus not x not y. Well, you'll need to, the y, this term is missing a y, which is needed for your sum of minterms. So you just add 1 and do x or not, y or not y, and then distribute it out, and then you have all your minterms. So any function can be expressed as a sum of minterms. Since any function can be expressed as a sum of minterms and max terms is the complement of minterms, then you can get to your minterms, complement it, and get your max terms. Okay. Whew. How are we doing? Yeah, we'll do this one too. Why not? We have A or B, A or not B and C. Okay, this one's missing an A, so we'll you're ANDing 1, so this is always going to be correct. You're allowed to do that, and then you just need to distribute out there. What's the problem with this guy? Well, it has the A, but he's missing the B or not B, and he's also missing the C or not C. All right, now you go crazy. So A, B, C, and then you're orient, you got A, B, and not C, so A, B, not C, or you have A, not B, and C, A, not B, and C, or you go A, not B, not C, not B, not C, and then we distribute that out, so then you have A, make that a better A, not B, C, or not A, not B, and C. And there I've converted this, which was not a sum of minterms, because each term has to have the 3 variables in it, to a sum of minterms by basically just adding 1 to each of the terms and expanding it out until I finally get to it. You got it, Jordan? No? You don't get anything? All right, besides Jordan, how are we doing?
That didn't sound enthusiastic.
Why are we doing this? We're trying to put it in a standard form so it'll be easier to manipulate later on. Yes?
Re-explain it one more time. I didn't quite get it.
Sure. So we have A or not B and C. This is not a sum of minterms because each term needs to have all 3 variables in it in order for it to be a minterm. So that is not a minterm, that is not a minterm. So we need to convert it to a sum of minterms. Well, how do we do it? We need to somehow add it. Well, the trick is to, well, here you're ANDing, so you AND 1 right here, and then you convert the 1 to A or not B, and then you multiply it out or distribute it out. He's missing 2, so you do it twice.
Got it.
And then you just distribute it out and it pops out.
Okay.
Yes. Perfect. Okay, so we ended up with, is that what I ended up with? 1, 2, 3, 4, 5, 6. Ooh, I got 6 of them. Oh yeah, hey, look at this. They're the same, so we don't need to write them twice. So it ends up being A or not B, and C is just minterm of 1 plus, or minterm of 4, or minterm of 5, or minterm of 6, or minterm of 7. Whew, I said plus. Or you can put this little sigma. Everyone got the sigmas? That's just the sum. 1, 4, 5, 6, 7. All right. You must use a little m so I know what you're talking about. It's a sum of minterms. Hey, look, since we can do the minterms, we can now complement it and get the product of max terms. It's the same trick, well, a similar trick, or you can just convert it to a sum of minterms and then complement the whole thing to get the max terms. Wow, that's a lot. But here's the important part. If f of x, y, z is the sum of minterms 1, 3, 5, 7, and you complement it, then you would get the sum of minterms 0, 2, 4, 6, or which ends up being the inverse, which is the product of max terms 1, 3, 5, 7. In other words, if you wish to complement the function, you change the sigma to a product, and you change the little m to a big M. We're done. Because of the way we encoded it. That's why this works. All right, I just explained this. So they're called the sum of products, or the product of sums. Whoo!
That makes sense.
Yeah.
I mean, that just flipped literally, so.
Right, yes. No, it makes sense to do it this way. Whew. Now, in this version, you are allowed to not, you don't have to write them all out in the sum of products or the product of sums, but you can't mix them like this. So in other words, in the sum of, what I was talking about earlier where this was not a sum of minterms, it is now a sum of products, because you only, you have your terms that are ANDed and you have ORs in between. That's why the sum of products is correct here and the product of sums is correct here. You basically have two layers of operations. In the sum of products, your outermost layer is the OR, your innermost, or your terms are product. On the reverse, your terms are ORed and they're, the terms themselves, are ORed and they're ANDed together. Or in other words, the outermost is the AND and the innermost is the OR. Keep in mind that you cannot mix them too much. Notice in here you have your outermost is an AND, so all your inner ones need to be OR, but that one isn't right there. Here your outermost is an AND, but over here we're trying to add an OR or an AND in between. Notice I've started using AND and OR interchangeably. It's because they keep using the word sum of products or products of sums. All right. Now that we have totally thrown too much terminology at you, I don't know what this slide is for, so we'll continue on. Oh, the reason for this is you can simplify it. Ooh, what does this simplify to? Apparently it simplifies to 3 literals. I'm going to run out of board space. ABC. For those of you who can't see, because I can't even see that, that's ABC. All right.
You should bring in one of those whiteboards on wheels, so that way you can ride on a whiteboard instead of a blackboard.
All right. Let's see if how much of this I remember how to do, or any of it. All right, we can take the BC out of these two guys. And we can take the AC out of this. Why is this? Oh, that's a C. Or no, we can't. We can take the AC out of that. this went over here, this guy went over here, brought him down. That's just one, so we have B, C, or, and that's just one, AC, or A, B, C, not. Hey, we can do the same trick again with, or can we? No, we can't. Well, we can take a C out of that, but that's not gonna help us. We can take A out of here, that's not gonna help us, but we can take the C naught out of that. Or, we can take the A out of that, sorry. Whoops. What was the theorem? We did this at the very beginning of class. And we can drop the C naught. And what's that? 1, 2, 3, 4, 5, 6. Hey, I got it down to 6. I wonder what I'd be missing. Don't know what I'd be missing there. All right. So I got it down to 6 terminals. They got it down to 3. So they're better at it than I am. Did they give me the answer? No. But that's the answer. And this should look very familiar from your previous assignments. Okay. So we've talked a lot of terms. I've thrown a ton of terms at you. Sum of minterms, product of max terms. Let's see, Boolean algebra. How can we obtain the simplest circuit? Well, right now we have to math it all out, which we're not all great at, to try and get a minimum cost. So the next part is going to deal with how do we actually minimize this automatically.